PhD, computer science from UCLA. Since 2001, has been a faculty member of the School of Electrical and Computer Engineering at Georgia Tech. His research explores architecture design, electronic design automation of 2D, 2.5D, and 3D integrated circuits. He's published over 400 papers. He's received Best Paper Awards from the IEEE Transactional CAD in the Design Automation Conference of 2023. He's an IEEE Fellow. He serves on the program manager at DARPA. I'm not worried. Come on.
Thank you. This one? Appreciate it. All right, so this talk is about utilizing the backside of an IC. Right? So it's already happening to add PDA, right? We're going to add voltage converter on the backside of it. So that's what this work is about. And this work is funded by SRC, Sung Kyu Lim and So standard structure, we're going to spend some time talking about the technology needed to enable backside PDN and also backside active devices. So we're going to use a very unique transistor called IOW device. So we're going to spend a little bit of time talking about the technology as well. And then we're going to talk about our methodology and results. So backside power delivery is happening today. So Intel has done it for the first time. This is following Samsung, same thing. IBM has provided all the fundamental research outcomes. So power delivery, passive routing is happening. Right? But then what about adding some active devices on the backside as well to manage power conversion, voltage management? Is that possible? It's not as easy as adding, just wires on the backside because you need to add transistors on the backside. So we started looking into how that could be done. So again, like I said, this is what's happening right now. We had polymer network wires on the backside. We have IDR. So we have done some research on the feasibility of that combination there on the backside. So let's look at interconnect technology first. Okay, backside, we're going to have metals. So in our setup, we have heterogeneous node mixed circuits. So the front side, we're going to use 3 nano devices and wires. And for that, we have PDK, predictive PDK, hooked in academic setting. And on the back side, we're going to use something more relaxed, 65 nanometer technology. With the help from IMAC, as they're working on this technology themselves. So next time we will have 3 numbers, maybe 1, 2, and 3. Then this table shows all the numbers, the specs, characteristics. The way we decided is to integrate transistors to the back side. We're going to have this device in between MB1 and 2. This is so-called back-end line transistor, so you can insert transistors in between metal layers, instead of using the substrate to create transistors. Then we're going to need capacitors, right? So we're going to use MB2 and MB3 to create capacitors. Now TSP is extremely important because these are the ones that are connecting the device on the front side as well as the device on the back side. So these specs we got from my back, it's pretty aggressive. The width is like 60 nano and the pitch of 500 nano. So they have demonstrated in their fab that's totally possible and mass produced. Transistors on the back side, right? Between the metal lines, right? In fact, this is one of the it wasn't one of the Jason Snyder here is working with my colleagues at Georgia Tech, open manufacturing of device. So it's called IW device, amorphous indium tungsten oxide thin film transistor. So these devices, right? So you can again create in between middle lines, right? So it's back of the line transistor. And then currently, their end device is more stable than B. cetera, et cetera. They can fabricate these devices at a relatively low temperature of 250. You don't need 1,000 degrees to activate the glucon, right? So this is a very, very important technology when you want to stack things on top of each other. The bad news is the transistor is very slow. Very slow. So the mobility is like 20 versus 1400 if you use silicon time. Right? So I'm working with Sung Kyu Lim. He's working on the process and manufacturing. And then Sung Kyu Lim is creating a compact model for these devices. Design flow. So what I do, right, in this collaboration setting, right, is they give us the compact model and then the interconnect technology specs, right? So what we do is then we're going to start with the fully done front side. And then, based on the spec and the requirements from the front side devices, we're going to start designing the back side. So we're going to first of all, decide upon the type of the idea devices, right? And also schematic, sizing. So we're going to do that at the first step over here. And then when we're happy with the simulation results, we're going to start doing the layout. We're going to lay out the IVR devices, and then we're going to then integrate them into the backside where we have already routed the PDM wires on the backside, and we're going to integrate the IVR too. Okay? Then we're going to do the entire system diagram. So our IVR architecture, right? So there's two main types of on-chip IVR devices. The first one is based on inductors, and the second is based on capacitors. Long story short, inductors are very, very hard to integrate on a chip. In capacitors, you can do it relatively easily, right? So because of other factors that give us the trade-off space between inductor-based versus capacitor, we decided to go with capacitor for now. So that's the schematic of our capacitor-based IVR, where we use 4 IWO transistors, right? 2 of them in depletion mode, and 2 of them in enhanced mode. Because we don't have the peak, we need to use this N to kind of simulate what P does. Right? And then we also need 2 capacitors, the whole thing. This gives us the ability to scale down the voltage from 1.4 down to 0.7 for this experiment. I know some of the other chips may require a larger delta, but then the experiment that we did is based on that 1.4 down to 0.7 2-to-1 down conversion. Okay? Here, when you are designing an IVR, you have 2 main goals. Well, there could be some more goals, but then the goals that we consider in this work is 2. The first is the efficiency. We're going to maximize the power coming out of power going in. Okay? And we're going to minimize the ripple, voltage ripple, right? Difference between the max and the min. And we want to make sure that the output voltage is at least 0.7. So based on these requirements, we're going to focus on the sizing. Right? So we're going to size these 4 transistors and 2 capacitors, and so we came up with 2 sizing options so that we can compare. Right? The first one, in fact, is based on 1 monolithic IVR, and then the other one is based on 10 smaller IVRs working together in an interleave fashion. So we spent quite a bit of time doing the sizing manually. And I guess we need to talk to David Cat about doing the sizing automatically. So that's exciting. And And once you're happy with your schematic, you're deciding the decisions, right? So we're going to start doing the layout. Right? So we have, first of all, created key cells, try and use it, put that in the library, and then change it based on our sizing changes, right? So we have created key cells for user, then recap, and then based on the schematic and then the key cells, we're going to start doing the layout, and we're going to make sure that it passes through the manuals, civics, and we're going to do simulation. So, while you write, you will see the actual layout. We did it again manually, and I mean, if it's helpful, you have to kind of, try and automate the layout generation itself. But for now, we spent, 2 weeks doing this layout manually. Now that I look at it, right, so the screen is kind of, it's missing some of the details, but there you go. That screen is worse than this one. I don't know why that's not wrong. Right, so you can see the capacitor is in there. It's not me. There you go, asymmetry happening. Difficulty of element layouts. All right, so then once you're done with the schematic design, sizing, layout, we're going to integrate it into the full chip. And we're going to do simulation. So, again, like I said, we're not going to use just one gigantic idea. We're going to split into multiple and then have them collaborate. So we're going to use interleaved clock signals to make some of these work at the same time, parallel execution, right? Individually, they're smaller than one monolithic IVR, but then they can work together to try and manage voltage level. So now experiment on using parallel. So then, of course, this is the layout of individual IVR units that I showed you. Then we have also done backside PDN routing using our tools. Use of NV1, 2, and 3. And then they will create some parasitics, extract them, and all these things together. Then we're going to do the full chip dynamic algebra analysis. And we'll look at 2 things. The ripple, right? And after that, they're on to the VD level, right? And then we also want to make sure that the current is, maximized. So these are 2 main things that we're going to look for when we do the IVR. Final layout here. So the front side, we're using the metal layers on the front side to do signal routing as well as clock routing. And then we're doing power delivery entirely on the back side. And the back side, of course, we have 2 things happening here. Backside metals are used to route the PDN signals. And then, of course, we're going to add in between NV1 and NV2 the IVRs, the 10 of them. So the numbers. So we have again 2 options, right? The first is just the one, gigantic IVR versus 10 smaller with them working together. I know you could do a lot more sophisticated comparison. This is the first, iteration of our effort here. So we can, improve this work in many different directions. But for now, we want to make sure that our PDK works, correctly, or simulations, the environment works correctly. So we just, use this opportunity to make sure everything is just produce reasonable result. So a lot of numbers, but then the thing I wanted to show you, right, is first of all, our smaller size IVRs are 10 times more than one monolithic one. And then the voltage output is better with 10 small devices working together. So for 5.8 versus 0.65. And then, but then, it's getting harder. And then, of course, the best result we have on the iodrop itself is with the 10 small IVRs interleaved, we were able to reduce dynamic iodrop quite a bit. So we're very happy. So, conclusion. So, we made first attempt to try and create PDK, make use of backside interconnect, backside devices, back on the line, integrated backside devices to create and simulate IVRs. And we demonstrated that indeed also works correctly, so we can use it into expand further into many different directions. So one thing that we got requested by times is, okay, so how does your on-chip backside IVR compare with off-chip IVR? A very natural question. Or what if you put your IVRs not on the backside, but then on the front side? The front side things are better, right? In terms of device performances. So different kinds of comparisons are being requested. Then of course we haven't done thermal analysis yet, so we're going to do it. And then again, as I mentioned earlier on, there are things that need a lot of manual effort, sizing and layout. And so we are definitely interested in making use of some of the analog automation innovations. So that concludes my comment. Thank you.
Any questions? I'll ask you a couple. So on slide 9, I didn't see where the other, it was confusing circuit to me because my eyes are bad. I didn't see where the second depletion was.
So the line, okay, this one. So this is.
That's depletion, right? Where's the other one?
Where's the other one? Okay, let's look the other one.
I couldn't understand the circuit.
Right, I don't want to be.
Okay. It has to be spent.
Yes.
So the question I have, having built a couple of these things, the capacitors are kind of a weak link to when they're leaky. So how leaky would they be being on the backside, and how would that change the model?
It will change the modeling quite a bit. We don't have a way to model the leakage in the capacitor current tool set, right? So that's one of the.
Okay, and another one is, the other thing that would be interesting is what type of noise would be injected, right? Especially at startup, right? So when you're starting up the regulator, you have a transient effect that could be a problem.
That's a very good point. We get those complaints from analog designers. Sorry, I'm a digital designer, but I'm definitely willing to look into those kinds of things.
Sorry, I wasn't a lot of designer. Are there any other questions? It's a great use of resources, though. So,
of course.
And would there be any problem with the clock being distributed to the bottom interface?
Although I didn't show in this presentation, we also have done backside clock routing as well. In fact, we presented that work last year at DAC. And then this year at DAC, we're collaborating with Lim and Bayu on improving the quality of the backside clock and power route stick out and stick in IDL in between.
So one last question.
Yes.
So what is the possibility of getting the mobility higher in other, so you're using Indian tungsten.
Of course, that's not the only choice.
Right.
If I look at other alternatives, Suma is not going to be very happy. But he also admitted, okay, there are some other tunnel alternatives that can improve the mobility on the backside, integrated in between ventilators. I need some further conversation with him to see whether.
Well, thank you very much. Let's thank the speaker.